So you think you understand boat hulls? Here's what every boat owner needs to know about hull physics that nobody's telling you. Your hull is creating a hole in the water that desperately wants to collapse, and you're burning 40% of your fuel just fighting that battle, while you're cruising at 25 knots. Your hull generates a low-pressure zone that's literally trying to suck you backwards. How insane is that? This phenomenon determines everything about your boat's performance. But here's the kicker. Those $200,000 performance boats with stepped hulls, they're deliberately creating air pockets under their hulls, turning physics upside down to go faster. Let me destroy everything you thought you knew about boats moving through water. Your hull doesn't push water out of the way like a snowplow. What's actually happening would blow the mind of every dock expert who's ever cornered you with their theories. Water is 830 times denser than air and essentially incompressible. When your hull moves forward, it creates a pressure wave that travels at about 4,900 feet per second through the water. That's the speed of sound underwater. This pressure wave tells water molecules ahead of your boat to start moving before you even get there. The water doesn't get pushed aside, it flows in streamlines around your hull, following the path of least resistance. Here's the physics that costs you thousands in fuel every year. Your hull creates two distinct wave systems. The bow wave system starts at your stern, and the stern wave system forms at your transom. These waves interact with each other, and at certain speeds they either cancel out, giving you efficiency sweet spots, or amplify each other, creating those fuel-sucking dead zones. This wave interaction follows the Froude number equation, where speed divided by the square root of waterline length determines everything about your efficiency. The real mind-bender. At displacement speeds, you're trapped inside your own wave system. Your hull sits in a trough between waves it created, and no amount of horsepower will push you over that bow wave. You hit what's called hull speed at 1.34 times the square root of your waterline length in feet. It's like trying to climb out of a hole that gets deeper the harder you try. But planing hulls, they cheat the system entirely by climbing on top of the water, escaping their own wave trap. That's why a 20-foot boat with 150 horsepower can outrun a 40-foot boat with 300 horsepower. One's planing, one's imprisoned by displacement physics. By the way, if you're finding these hull physics revelations fascinating, smash that subscribe button right now, because we're about to expose why the most expensive hull design might actually be the worst choice for your boating style, something the manufacturers definitely don't advertise. Now we're getting into the controversial stuff that'll have people arguing until the marina bar closes. There are three main planing hull categories, and each one manipulates water flow using completely different physics principles. Deep V hulls with dead rise angles of 20 to 24 degrees at the transom are the smooth riders everyone raves about. But here's what they don't tell you. That comfort comes from constantly breaking water adhesion. You're literally paying a 15 to 20% fuel penalty for that smooth ride, because the V shape creates more wetted surface area and can't develop the same lifting pressure as a flatter hull. A 22-degree dead rise hull has roughly 25% more wetted surface than a 15-degree hull at the same displacement. That's like dragging an invisible parachute made of friction. Modified V hulls, running 15 to 19 degrees of dead rise at the transom, are where physics gets interesting. They transition from sharp entry at the bow, maybe 45 to 55 degrees, to those flatter sections aft. This gives you wave cutting ability forward and lift generation aft. But here's the engineering secret. That transition zone, called the chine flat, is where 60% of your lift generates at planing speeds. Mess up that transition angle by even 2 degrees, and you've created a boat that porpoises uncontrollably. Flat bottom and semi-flat hulls, 8 to 14 degrees dead rise, are the acceleration champions, but they're also the most misunderstood. Everyone thinks they pound in waves because they're poorly designed. Wrong, they pound because they're generating maximum dynamic lift with minimum wetted surface. That jarring impact, it's the price of physics-defying efficiency. These hulls can plane at speeds 30% lower than deep Vs of the same length. A flat-bottom John boat gets on plane at 12 miles per hour, while a comparable deep V needs 18 miles per hour. That's not poor design, that's purposeful optimization for specific conditions. Stepped hulls are where boat building enters the aerospace realm, and where traditional naval architects start sweating. By creating transverse steps, essentially notches running across the hull bottom, you're introducing air under the running surface, reducing wetted area by 20 to 35%. Sounds amazing, right? Here's what the brochures leave out. Each step creates a controlled ventilation cavity. Air gets pulled under the hull at atmospheric pressure, while water pressure around it is higher. This pressure differential creates lift without wetted surface. Essentially, you're hydroplaning on cushions of air trapped between water surfaces. Racing boats with 3-step hulls can hit 150 plus miles per hour, with the same power that would push a conventional hull to maybe 100 miles per hour. But here's the engineering challenge with stepped hulls. They're incredibly sensitive to operating conditions. That air cavity that gives you speed, disturb it with the wrong trim angle, weight distribution, or turn radius, and you've got instant instability. The hull can huck, sharp, uncommanded turn, or experience blowover, becoming airborne with zero warning. Professional racers call it checking out. 1 second you're in control, the next you're hoping your life insurance is paid up. The tolerances are brutal. Step height needs to be within 1/8 of an inch of optimal, step angle within 2 degrees, and the distance between steps calculated based on your specific running angle and speed range. Get any parameter wrong and you've built an expensive submarine. That's why most production stepped hulls are actually just marketing gimmicks with cosmetic notches that don't create true ventilation cavities. Real steps require precision that would triple manufacturing costs. Let's talk materials, and I'm going to tell you why that bargain boat might cost you triple over its lifetime. Fiberglass dominates 70% of the recreational market, but fiberglass is meaningless without specifics. Hand-laid fiberglass uses chopped strand mat and woven roving, creating a hull that's 30 to 35% glass fiber by weight. Sounds decent until you realize that means 65 to 70% is polyester resin, and resin is what degrades first. Those spider cracks appearing after 3 seasons, that's resin breaking down from UV exposure and flex cycles. The serious builders use vacuum infusion or resin transfer molding, achieving 50 to 60% fiber content with vinyl ester or epoxy resins. This isn't just stronger, it's 20 to 30% lighter for the same strength. Weight is everything in hull performance. Every 100 pounds of reduction equals roughly 1 mile per hour in top speed, and 5% better fuel economy. That $10,000 premium for vacuum-infused construction, you'll recoup it in fuel savings over 5 years if you boat regularly. Aluminium hulls are the workhorses nobody discusses, honestly. Marine-grade 5086 aluminium has a strength-to-weight ratio that embarrasses fiberglass, and it's infinitely repairable with basic welding equipment. But here's what manufacturers hide. Aluminium suffers from fatigue cycling, unlike steel, which has an endurance limit. Every flex cycle accumulates fights damage, and salt water accelerates galvanic corrosion when dissimilar metal meets. That lifetime hull warranty. Check the fine print about salt water use and inspection requirements. Carbon fiber is the exotic everyone fantasizes about. 5 times stronger than steel at 1/5 the weight, with stiffness that makes aluminium look like rubber. But here's the engineering reality. Carbon is brittle under impact loads. It doesn't dent or crack, it can catastrophically fail. A carbon hull hitting a deadhead doesn't get a ding, it can literally shatter. Plus, carbon conducts electricity and blocks radio signals. Those $5,000 carbon race boats, they need special grounding systems and external antennas for basic electronics. Still following along? Perfect, because understanding this next section about hull bottom technology could save you from making a $50,000 mistake. Hit subscribe and the notification bell, because we're revealing industry secrets weekly that dealers pray you never discover. The shape of your hull bottom determines how water releases from the running surface, and this is where 90% of boats are compromised by manufacturing economics. Sharp chines with true 90-degree angles give clean water separation, reducing drag by 10 to 15%, but they're expensive to mold and create stress concentration points. So manufacturers use rounded chines and tell you it's for comfort. Reality, it's for production efficiency and warranty claim reduction. Strakes, those longitudinal ridges on the hull bottom, are the most misunderstood feature in boat design. They don't just provide lift, like every salesman claims. They create controlled vortices that energize the boundary layer, keeping water attached to the hull longer before separation. This delays flow separation and improves directional stability. But here's what's crucial. Strake placement is critical to within half an inch. Position them too close to the center line and they increase wetted surface without benefit. Too far outboard and they create unpredictable handling in turns. Pad hulls, where the aft center portion extends below the outer hull sections, are pure physics exploitation. The pad runs in solid water while the outer sections run in aerated water from the pad's turbulence. This reduces effective wetted surface by 20 to 25%, but creates a knife-edge handling characteristic. The boat tracks straight until you exceed the critical slip angle. Then it spins like a top. Competition boats love them. Insurance companies specifically exclude them. Ventilation plates, lifting strakes, and hull relief slots all manipulate airflow beneath your hull. That innocent-looking relief notch behind your strake, it's calibrated to introduce precisely enough air to reduce surface tension without causing loss of control. Block it with bottom paint or marine growth and you fundamentally altered your hull's performance envelope. I've documented boats losing 8 miles per hour from painted-over ventilation features. The physics of how your bow enters waves determines whether you're enjoying the ride or scheduling dental work, and the aggressive-looking designs often perform worse than subtle shapes. Carolina flare, that concave curve seen on sport fishers, doesn't just deflect spray, it creates a compression cushion by trapping air between the wave face and the hull. This air spring can reduce vertical acceleration by 40%, but here's the engineering trade-off. It only works within specific encounter angles. Hit a wave outside that 15 to 30 degree sweet spot and that flare becomes a brake, killing your forward momentum. The axe bow trend in performance boats is pure physics optimization for one parameter: speed maintenance in chop. By eliminating flare, you minimize the hull's tendency to climb wave faces. The bow slices through rather than over, maintaining velocity in conditions that would slow conventional bows by 40%. But you're trading reserve buoyancy for performance. An axe bow that submarines has no recovery mechanism. The physics that make it fast also make it unforgiving. Fine entry versus full entry is where hydrodynamics meets economics. Fine entry, sharp bow angles under 20 degrees degrees cuts waves better, but provides minimal forward buoyancy, making the boat wet riding and prone to submarining. Full entry, broader bow, 25 to 35 degrees, provides more lift and a drier ride, but impacts waves harder. The optimization point is entry angles of 20 to 25 degrees for rough water, 25 to 30 degrees for protected water speed. Outside these ranges, you're fighting fluid dynamics instead of leveraging them. Wave-piercing bows, adapted from naval swathe designs, are appearing on high-end center consoles. Instead of riding over waves, they penetrate the upper portion, while the main hull body passes over the wave base. This maintains speed in sea states that would slow conventional hulls dramatically, but the mathematics are unforgiving. The piercing section volume must be precisely calculated for your displacement and operational speed range, or you'll submarine at the worst possible moment. Stability and maneuverability exist at opposite ends of the physics spectrum, and every hull design chooses a point on that continuum. Here's what naval architects calculate but rarely explain to buyers. Initial stability, how stable the boat feels at rest, comes from beam width and hull form coefficient. Wide, flat hulls feel rock solid at the dock but can become dangerously unstable dynamically. That 24-foot deck boat with an 8.5-foot beam, its center of buoyancy shifts dramatically with heel angle, creating a metacentric height that actually decreases beyond 20 degrees of heel. Translation: it feels stable right until it flips. Ultimate stability, maximum heel angle before capsize, is what keeps you alive when conditions deteriorate. Deep V hulls have progressive stability curves. Resistance increases with heel angle up to 50 to 60 degrees. Flat hulls have regressive stability. They become less stable as heel increases, with negative stability possible beyond 35 to 40 degrees. This is why offshore boats use deep Vs despite the efficiency penalty. That extra fuel consumption is your stability insurance premium. The center of gravity versus center of buoyancy relationship governs everything about vessel dynamics. Raising the center of gravity by just 6 inches, like adding a second station hardtop, can reduce your positive stability range by 12 to 15 degrees. That's the margin between recovering from a beam C and capsizing. Every 100 pounds added above the waterline needs 300 pounds of ballast below to maintain the same stability characteristics. Maneuverability derives from how quickly you can overcome directional stability. Sharp chines provide lateral resistance in turns, acting like rails. Rounded bilges allow progressive sliding. But here's the physics few understand. At planing speeds, your hull's directional stability increases with the square of velocity. At 40 miles per hour, your hull's gyroscopic stability is 16 times greater than at 10 miles per hour. This is why performance boats require power-assisted steering as necessity, not luxury. The uncomfortable truth about boat safety is that most design decisions prioritize liability protection over optimal safety. Understanding the actual physics helps you compensate. Foam flotation requirements are inadequate from an engineering standpoint. Coast Guard regulations require sufficient flotation to support the hull weight, not your engines, fuel, gear, and passengers. Your unsinkable boat will technically float, inverted or awash, but floating. The foam calculation assumes empty weight. Add realistic loading, and that level flotation rating meets minimal federal requirements while you swim. Self-bailing cockpits only self-bail under specific conditions. The scuppers require water velocity past them to create venturi suction. Stationary, that water stays put. Overloaded aft, the scuppers drop below waterline, becoming flooded ports. I've documented boats sinking at anchor when scupper flapper valves failed, turning drains into 2-inch water intakes. Hull structural integrity in impacts is where modern construction fails catastrophically. To reduce weight and cost, manufacturers use cord construction, foam or balsa wood sandwiched between thin fiberglass skins. This provides excellent stiffness-to-weight ratios until water infiltrates the core through fastener holes or impact cracks. Then your hull becomes a waterlogged sponge, losing 50% of its strength while gaining hundreds of pounds. A decade-old cord hull can fail from impacts that solid laminate would survive easily. The sobering reality: most production boats are engineered to meet minimum standards at maximum profit margins. They calculate structure for calm water, despite knowing you'll encounter 4-foot seas. They specify components for average loads, knowing you'll occasionally hit extremes. They're betting warranty expiration beats fatigue failure, and statistically, they're usually right. Different applications demand different physics solutions, but marketing has so confused this that people routinely buy completely wrong hulls for their actual needs. Bay boats exemplify design honestly. That 15 to 18 degree dead rise and wide beam isn't about deck space, it's about maintaining plane at slow speeds in shallow water. The physics requirement is generating sufficient lift at 18 miles per hour instead of 25 miles per hour. Every design element follows from that requirement, but manufacturers market them as stable fishing platforms, leading buyers to take them offshore where that moderate dead rise becomes a kidney-destroying liability. Wake boats deliberately violate every principle of efficient hull design. They're optimized to create the biggest, cleanest wake possible by displacing maximum water inefficiently. That deep hull with no lifting strakes. It's supposed to plow, not plane. The ballast systems adding 2,000 to 4,000 pounds. They're intentionally sinking the boat to displace more water. You're burning 6 to 10 gallons per hour to go 20 miles per hour, because that's what physics demands for a surfable wake. Bass boats represent pure physics optimization for protected water speed. That 70 plus miles per hour capability comes from minimal dead rise, often 10 to 12 degrees, maximum beam for dynamic stability, and lightweight construction, pushing structural limits. But here's what's unspoken. They achieve this by operating at minimum safety factors. That's why identical length bass boats carry 250 horsepower ratings while bay boats max at 150 horsepower. The bass boat isn't stronger. It assumes you'll never encounter real waves where that optimistic engineering becomes catastrophic. Your boat's hull is a complex physics equation balancing opposing forces: speed versus seakeeping, stability versus agility, efficiency versus capability. Every curve, angle, and material choice represents a decision about which compromise to accept. The marine industry profits from keeping these physics principles opaque, selling revolutionary designs that are simply different optimization points on the same fundamental curves. They know most buyers fixate on top speed and styling, not understanding they're shopping for the wrong physics solution to their actual boating reality. But now you understand the science. You know that dead rise angle determines your ride quality tax, that stepped hulls trade forgiveness for speed, that bow shapes affect more than aesthetics. You understand why that bargain flat bottom pounds, why that expensive deep V drinks fuel, and why every hull design is perfect for someone, but wrong for someone else. Most crucially, you realize there's no universal optimum, just the right physics compromise for your specific waters, speeds, and usage patterns. Find that sweet spot through honest evaluation of your actual boating, not your boat show fantasies. If this deep dive into hull physics opened your eyes, hit that subscribe button immediately. We're exposing marine industry secrets every week, translating engineering reality into knowledge that'll save you money and keep you safe. Ring the notification bell, because next week we're revealing why your boat's electrical system is a ticking time bomb, and the simple physics that predicts exactly when it'll fail. Until then, keep your bow up and your dead rise appropriate. This is your source for unfiltered marine engineering truth, signing off.